the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a final video in a series on linear independence for vectors from vector spaces and bases of subspaces. This requires your knowledge of null space and column space. We're actually going to step back into a conversation about matrices here. So our previous videos that we've gone through have kind of stepped away from matrices and talked about bases of vector spaces or subspaces of vector spaces that are built upon vectors not representable by column matrices. For example, the subspace P sub 2 or something like that. And if you already know that you can represent elements of this subspace as column vectors, that's okay. That's just a future topic for us in the course that I teach. Anyhow, stepping back into a conversation about matrices, we're specifically going to talk about bases for the null space and column space of a given matrix in this video. A basis for the null space of A consists of the linearly independent vectors found to span the null space when solving AX equals 0. Now, we've talked about that so much already in previous videos. There's not much else I need to say about that theorem. It's not really in the text that I use. I just write this theorem down so that my students have access to it. But the reality is you should pretty much be comfortable with this concept at this point. Recall the null space for a given matrix A is a set of solutions to the homogeneous equation AX equals 0. And all this theorem is saying is, if you have a basis for that null space, well, obviously, it's going to be linearly independent vectors that span the null space. That's from the definition of a basis. There's not much else I really need to say there. But it would be good for us to go through an example to find a basis for the null space of a given matrix. Now, this matrix will look familiar to you if you've been following my video series. If not, that's no biggie. We can actually treat it as though we've never seen it before. So find a basis for the null space of this matrix. Just like we mentioned when talking about the null space of a given matrix, it is very challenging to actually look at a matrix and identify the null space just from a given matrix. And that's from this table right here, which is a comparison and a contrast between the null space of a given matrix and the column space of a given matrix. The green highlighting is for the easier tasks, and the pink highlighting is for the more challenging tasks. Well, if you look under the null space of A, any of these in 2, 3, and 4 kind of describe why it's going to be difficult for us to identify the null space given a matrix. Probably the best one to say is number 4. There's just no obvious relation between the null space of A and the entries in A. And number 3, it takes time to find vectors in the null space of A because row operations on the augmented matrix A0 are required. So that's what we're actually going to do in our current situation. We'll go ahead and place this matrix in an augmented matrix and row reduce. And there's our reduced row echelon form of the augmented system A0. And this allows us to see that we have 3 free variables associated with those columns right there. Now we have a theorem from the past that says that the number of vectors in the spanning set for the null space of A should be the same as the number of free variables in the equation AX equals 0. So we should have 3 vectors in the spanning set for the null space of A. That is 3 vectors in the basis for the null space of A. Let's go ahead and write down our relations here. And let's go ahead and write the representative vector for any vector in the null space. So that's the parametric vector form of the solution to this homogeneous equation AX equals 0. And those 3 vectors right there span the null space. They're also linearly independent, so therefore a basis for the null space of A is the set of those 3 vectors. So the work done in finding the basis for the null space of a given matrix is the same work you're going to do to find the spanning set for the null space of a matrix. Basically what we did before, solve AX equals 0, write the solution in parametric vector form, and then those vectors, which are linearly independent and span the entire null space, form your basis for the null space. But to find a basis for the column space of the matrix is, well, not more challenging, but has a little bit of a trickiness to it. Remember, the column space of a matrix is the set of vectors that are the result of the product A times an arbitrary vector X. It's basically all linear combinations of the columns of A. In fact, that's how it's defined. Something very special about this matrix, because it's going to be important for a future conversation, like within a few moments, is that if you think about all possible linear combinations of these columns, there's no such linear combination that would produce, for example, the vector 6, 1, 7. There's just no linear combination of those columns that can give you that 7 in the third entry of that vector. So from a quick observation of this matrix, we do know that the column space is not going to be all of R cubed. It's actually going to be R squared. In other words, this can create any combination of vectors where the first two entries of the vector are non-zero or could be 0, for example, but the third entry must be 0. It is essentially creating a subspace R squared in the vector space R cubed. Now, I did mention finding the basis for the column space of a given matrix might be somewhat tricky. However, I also mentioned in a previous video that working with the column space of A is somewhat easy when you're just asked to find the vectors that generate the column space of A. Because by 4 here, there's an obvious relation between the column space of A and the entries in A, since each column of A is in the column space of A. And by number 3, it says it's easy to find vectors in the column space of A because, well, the columns of A are being displayed to you. All other vectors in the column space of A are formed from them. So we just need to find a linearly independent set of those columns from A to create a basis for the column space of A. And looking at this matrix, a linearly independent set of our columns is just going to be the first 2 columns. It actually is pretty easy. So why did I tell you it's a bit tricky? Well, you'll see in a moment, but let's go ahead and just write this down formally. There we have it. The set of vectors 1, 0, 0, 5, 1, 0 form a basis for the column space of A. And this was somewhat obvious because we did not have to do any row operations to identify the pivots. But once you identify the pivots, you sort of know at that point that those columns containing the pivots are 1, linearly independent, and 2, generate all other columns in this matrix, and also all vectors in the column space of A. So what is the generalized tactic for finding the basis of the column space? Well, in general, once we're given a matrix and somebody says, I need the basis for the column space of this matrix, we will use row operations on that matrix to find the pivot columns. Now, like I said, in this case, we didn't have to use row operations because somebody handed us a very nice matrix that has already been row reduced to an echelon form. But once you've done that row reduction and found the pivot columns, and this is the tricky part, the basis for the column space of A is going to be the collection of pivot columns from the original matrix A. So again, in this case, we didn't have to perform row operations to get this down to an echelon form, but had we been forced to perform row operations to find the pivot columns, once we find those pivot columns for the row reduced form, so we do a lot of work to get down to, let's say, some matrix B that is row equivalent to the matrix A. Once you find those pivot columns in B, your row echelon form of A there, what my list below is telling you is that those pivot columns are not actually the basis for the column space of your original matrix. You have to go back to your original matrix, find those corresponding pivot columns. Those corresponding pivot columns in your original matrix are going to be the basis for the column space of that original matrix A. And I'll show you this in a very, very obvious example in just a few moments, but I want to lay down the theory, so we're just going to view the theory very quickly. So from the null space conversation, the null space of a matrix is invariant under row operations of the matrix. That is, the solutions to the homogeneous equation AX equals 0 do not change when performing row operations. Now, that is a theorem from like the first week of your linear algebra course, that when you perform row operations on a linear system, the solutions to that system are invariant. That is, they do not change when you perform row operations on that linear system. So this theorem is actually not new, it's just the wording is new. Instead of saying the solutions to AX equals 0 don't change when you do row operations, we're saying the null space of a matrix, which is the set of solutions to AX equals 0, is invariant under row operations. So there's nothing really new there. So somebody hands us a matrix and says, I need to know what the null space is. We know we can augment that matrix with the 0 vector and perform as many row operations as we want to find the parametrized vector solution for that homogeneous equation AX equals 0. And those vectors that form the parametric vector solution to that homogeneous equation are going to be linearly independent, and they're going to span all the set of vectors that are solutions to AX equals 0. However, here's the warning. We're not so lucky when it comes to the column space of a matrix. And I should say we're somewhat lucky when it comes to the column space of matrix, because the column space is very easy to identify when handed the matrix A, versus the null space of a matrix. You actually have to do work. No matter what, you have to solve the homogeneous equation. The column space of a matrix, generally speaking, is just looking at the matrix and saying, oh, the column space is a set of vectors that are linear combinations of these columns in this matrix. All I need to do is reduce these columns down to a linearly independent set of vectors, and that's done by finding the pivot columns. So there is a little bit of work here to find the basis for the column space, but actually to talk about the column space is pretty easy. The column space of A here is just all the vectors generated by linear combinations of all of these columns, which really reduces down to just linear combinations of these two columns, because those are a basis for the column space of A. And that leads us to this theorem right here. The pivot columns of a matrix form a basis for the column space of that specific matrix. And that's incredibly important, because the implication of that statement is if you perform any row operations on it, well, the relationship between the basis of the column space of your original matrix and the basis of the column space of your brand new row reduced matrix, well, there's not very much in the way of a relationship there, honestly, except that they share the same pivot columns. But the structure of those columns may differ wildly. And that's what our next example is all about. We're going to illustrate this. Now, without showing you the wording up above, I'm just going to say, let's find a basis for the column space of this matrix. And by the previous theorem, if I knew the pivot columns of this matrix, I would just highlight those and say those are the basis vectors for the column space of this matrix B. But I can't identify the pivot columns as written. So what I need to do is perform a little bit of row reduction. And we arrive at our row reduced form. If I highlight the pivot columns in the row reduced form, we see column 1 and column 2 are pivot columns. Therefore, columns 1 and 2 in the original matrix are pivot columns. Now, just for the time being, I want to call this row reduced form, I'm going to call this A. And the reason why I'm calling that A is because I want to draw your attention to a previous problem that we've done. That matrix A is from our example early in this video, and we found that the basis for the column space of this matrix A is going to be 1, 0, 0, 5, 1, 0. And we had made a critical mention here. Notice that no matter what we do with linear combinations of these columns, we can never generate the vector 6, 1, 7. So 6, 1, 7 is not in the column space of this matrix at all. However, despite the fact that 6, 1, 7 is not in the column space of this matrix, 6, 1, 7 definitely is in the column space of the original matrix. If you multiply that matrix by the vector 1, 1, 0, 0, 0, you will get 617 as your resulting vector. So 617 is in the column space of the matrix B, but not in the column space of its row reduced matrix. This should be very impactful because this should tell you that the column space of a matrix will change when you perform row operations. And that's critical because once we have found the pivot columns via row reduction methods, well, the pivot columns don't change. So given a matrix, it doesn't matter how many row operations I do, the pivot columns will always be the same pivot columns. No matter how many row operations are performed, I know that in matrix B, the original matrix, the pivot columns are the same as the pivot columns in matrix A. They're columns 1 and 2. And remember, the pivot columns are going to form a basis for our column space. So the basis for the column space of B here is a set of vectors 101, 516. Those two vectors will generate all vectors in the matrix B and all vectors in the column space of B. Specifically, they'll generate that 617 vector that comes out when you plug in this vector 11000. Now let me zoom out to read the original problem. Show that the basis for the column space of A from the previous example is not the same as the basis for the column space of B given below, despite A and B being row equivalent. Yeah, I didn't want to reveal that at first, but now you can see they're definitely not the same bases. The basis that I highlighted here and the basis that I highlighted up here, they also don't generate the same exact space. So very, very interesting example to round out this video and actually to round out this entire lecture series on linear independence of vectors and vector spaces and bases. Bases of subspaces is going to dominate a lot of our conversations as we move forward. So you have to kind of get used to them. I would spend a lot of time doing extra problems in your assigned work from your professor so that you are well prepared to work with bases as you move into examinations and whatnot, because they do, like I said, dominate a lot of linear algebra from this point forward. All right, that's it for me. You guys have a wonderful day. Be awesome human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.